Okay, Bismillahirrahmanirrahim. So, this is the second segment of this lecture. So, it has said that the wisdom is the lost property of the Muslim, of the believer, and so wherever you find it, you can take it. Now, recently, after the global financial crisis, a lot of people asked, how come economists completely failed to see this? They are supposed to know about economics. So, one of the economists, many have said things, but Krugman said that economists as a whole mistook the beauty of mathematics for truth. And this is actually true in the sense, this is one part of the truth, that the economists do a huge amount of mathematics and they don't understand what mathematics is. They don't understand how mathematics relates to reality. Actually, strangely enough, the philosophy of mathematics was described by Umar Khayyam very clearly, and it is a philosophy which still has not been understood in the West. He used this philosophy to create what is now known as Cartesian coordinates, which is analytic geometry, which was actually a revolutionary concept in mathematics. It combines algebra and geometry. It was created by Umar Khayyam. It has been attributed to Descartes. If you look at Wikipedia, it says, strangely enough, not Wikipedia, another article, I have it on the website. This Descartes never talked about Cartesian coordinates in his life. So in this and in many other things, there is this Indian mathematician C.K. Raju. He has said that this is a common pattern, that they steal material from other cultures and then instead of attributing it to the original, they attribute it to someone at random. So Descartes never did anything with Cartesian coordinates. And in fact, if you look at his works, but Umar Khayyam did, and he explained what it is, and he explained very specifically. So actually, mathematics is also a creation of Allah, and it is an abstract creation. So it is there is a world, an ideal world, an imaginary world in which mathematical truths lie. Like if you see the circle is perfectly round. Now nothing like that exists in the real world. So when we study mathematics, we are studying an imaginary world, but there are real truths in that imaginary world. Who created them? Allah Ta'ala did. So in order to understand mathematics, we have to again look in two places at the same time. And this is something that you have not been taught because it is not known in the West. And this is why it is difficult to understand mathematics. And what I want to do is actually, but actually people who are mathematicians, they intuitively understand this. So they can get, from the body they can get to the soul because it is in the heart and mind of every human being. Allah Ta'ala created all of us with the ability to understand and to appreciate mathematics. This is the thing that it goes into if you can appreciate, understand the beauty of something, then it is the heart which can appreciate beauty. The mind doesn't see the beauty. That's logic. So what I would like to do is to teach you to appreciate the beauty of mathematics. So, but before that you have to, and we'll do this. So there are some general principles. Like right now, all I am saying is all general principles. You cannot understand a general principle unless you see it illustrated in a very specific case. So, for example, if I say that the commutative law is that x plus y equals y plus x. So this is abstract, and this is algebra. And algebra was invented by Al-Khwarizmi. And this was a great accomplishment. The everybody understands that, okay, 2 plus 3 equals 3 plus 2. But the fact that this is a principle and it can be expressed in abstract terms, this is the accomplishment of Al-Khwarizmi. Now, for example, so there is the general principle is x plus y equals y plus x, but this and all general principles, whether it's in philosophy or economics, that free markets are good, in order to understand them, you have to translate to a very specific, concrete context. And unless you do that, you will not be able to understand general principles. So, but at the same time, the concrete and special thing is just one example, and the general thing is a lot of different examples and a pattern which exists in a lot of different examples. So, in order to understand the general philosophical principle, the abstract mathematical concept, you must be able to reduce it to a particular one. And the ability to have the simultaneous knowledge of both is the understanding that is required. And this is what is missing, because in your teaching you are either taught one or the other and the connections are not made. So in this course you will be trying to do both at the same time. So see the general principle, see the concrete application. Same thing, abstract and concrete. Now algebra and geometry. Geometry is visual, you can see it. Algebra is notational, it's harder to see. There is a story about Ramanujan, who was an Indian mathematician, and he could see truth, and actually there's a movie about him. So he wrote down a lot of theorems that this is true, this is true. And then he sent them to Hardy, who was a mathematician in Oxford or Cambridge or somewhere. So he was amazed, because actually some of the things that Hardy had written, he said that these are wrong, and he found that yes. So he invited him to come to England, and he went to England, and then they tried to figure out that what is going on, in the sense that they asked him, well, okay, this is your theorem, but how do you prove it? He had no idea what a proof is. So, but he could see it. He could see the truth. So this is the thing that I was trained in the proof tradition, and for a long time I used to believe that to understand a mathematical theorem means to be able to write down a proof. It was much later that I realized this is completely wrong. To understand a mathematical theorem is to understand the concept. You may not and to visualize, to be able to see what the theorem is saying, not to be able to write down a sequence of steps of proof. So I had to unlearn this. So how to see truths? Now, to explain this. Now, this is an abstract concept. Now, I'm going to explain this in concrete terms. So, if you take two fractions, I can teach you how to add them. Okay, what you do is you multiply the denominators, and then you cross multiply, and then you add the numerators and put the denominator. Okay, here's the rule. What does it mean? You have no concept. I mean, with this method, you have no concept. So this is the proof, and this is the mechanical understanding which you have been taught in all your courses. But the concept, well, suppose I want to add 1/2 and 1/3. So instead of saying multiply 2 by 3 and put 2 on one and 3 on the other, I say, okay, take a pie and cut it into 6 slices. And now, how much is half of the pie? Well, that's 3 slices. And how much is 1/3 of the pie? Well, that's 2 slices. So if we take 3 slices and 2 slices, we have 5 slices. That's 5/6 of the pie. Now you have understood it. And there is no rule. If I explain to you with the pie, you haven't understood how to add fractions. So the concept of the addition of fraction is different from the mechanical rule. Both are important. I mean, if you understand the concept but you don't know how to add fractions, that's not very useful. But you need to understand both. You need to understand the concept and how to execute that concept. But if you have to understand only one, then the concept is better. and the concept is clear and understandable to everybody. The rule, it is just, and you have been taught when you teach too many rules that this is how you do this, this is how you do this, then you say, okay, my mind is useless, I just have to learn to follow orders. And so this is what actually breaks your heart and breaks your ability to think. So actually, there is a book by Kahneman, Thinking Fast, Thinking Slow. It says that actually we have two mental systems. One is a fast system, which immediately sees a situation and comes to an immediate conclusion without actually going through analysis. That if you are a driver, then you know that you are sometimes when something strange happens, you respond before actually analyzing what has happened. The logical analysis doesn't know you hit the brakes or you turn the wheel before actually understanding what's going on. The image impacts your eye and you act in response to this without thinking about, okay, this is happening and that is happening. So there is thinking slow, which is a logical process step by step. And so those two are different systems of the brain. So intuition is system one, which is fast. You see the picture and you understand. And then the logical process is a different. And these two are separate. So intuition and the beauty of mathematics is understood by the intuition, by the heart, by the visual picture. So today, when we start on mathematics, you should be very excited, because what we are going to do is that there are centuries of work have gone into this theorem that I am going to first prove, which is some theorems about algebra. What I am going to do is to try to explain some very beautiful facts about the roots of polynomials. And these facts were discovered by over centuries. And actually, very strange, if you look at the Wikipedia entry on Umar Khayyam, it says that Umar Khayyam solved the cubic. Now actually the cubic equation, which we will actually deal with, not in this lecture but in the next, is quite difficult to solve. And all of these mathematics books were translated into Europe, and it took them centuries to understand and learn these things. And nowadays, if you look at the Wikipedia entry for cubic equation, you will see that Cardano in Italy solved the cubic equation. Even though the books were there and they studied, and they actually, for a while, they couldn't understand what they are saying, and it took them quite a while to rediscover the truths. But still, they are misattributing, as usual, the Raju thesis that they have stolen. Actually, there's a whole book called The Theft of History by Jack Goody, in which he says that the Europeans took the inventions from many different civilizations and claimed them for their own, attributing in fact, just like I've said that the cubic equation is being attributed to Cardano, when in fact it was discovered by Umar Khayyam. And Cartesian coordinates, again, due to Umar Khayyam, claimed by Descartes. And then the most amazing thing is Copernicus, who copied from Nasiruddin al-Tusi everything that he had. And now it is said that, and actually he made some mistakes in his copying, and he didn't understand fully the mathematical system. And so later his successors, see, this is the test for plagiarism, that if I have two students and both of them have the same answer, now I want to find out who has copied from whom, I will say, okay, put away, and you explain to me what the answer was. So the student who wrote the answer, he will be able to explain, and the other one will make mistakes. So there are many ways in which you can find out that they plagiarized. So actually, the results that we are going to study, it took centuries for people to get. Now we are going to get them in a very short time. So you should feel excited that these are treasures which have been gathered over centuries, and now we are going to get them for free. Again, another example that this is again from the from Wikipedia. This is copied from Wikipedia. Al-Hazen did what we would call integration. So in another place they say, well, differentiation of certain types was known to Arabs, and integration was known, and infinite series was known to Indians, but Newton and Leibniz invented calculus. And actually in a discussion, in a footnote, he says, yes, it is true that people had all of these parts, but Newton and Leibniz put it all together, and so we don't need to go back and revise history and say that actually calculus was invented before. So this is just any complete injustice, and actually so calculus was not invented in Europe, but it is claimed by Europeans. So our first step, which may not be completed today, is to prove the fundamental theorem of algebra, which is one of the most beautiful results in all of mathematics. And it's very simple to state. One sentence, it says there, every polynomial of degree n has exactly n roots. But it is very difficult to prove, and it took centuries to arrive at the correct understanding of what this is, what it means. So this is going to be our goal, to prove that every polynomial of degree n has exactly n roots. And not just to prove it, proving is trivial part, to appreciate the beauty of this result. This is the thing. So first of all, what is a polynomial of degree n? So this is defined here. It is a, yani you have a n times x to the n. This is nth degree term, a n minus 1 times x to the n minus x raised to the n minus 1 power, all the way up to a0 times x to the 0. What is x to the 0? 1. So this is just a constant term, but it is just to show, again, putting x to the 0 just makes it more beautiful, because you see that it's all, if I take out the x to the 0, it is still correct, and in fact that's how you usually write it, but then you miss the beauty of it, because everything is the same. So now one crucial condition for it to be of degree n is that an must not be 0. This is very important, right? If an is 0, then it looks like a polynomial of degree n, but the degree n term is not present, so it is not actually of degree n. So now let's look at now we are going to prove the fundamental theorem. So we start with 0. So now what is the polynomial of degree 0? It's a0 times x to the 0. a0. How many roots should it have? 0. Now how many roots does it have? Do you know what a root is? Of course, I haven't defined that. I will define that later. A root is a value of x for which the polynomial itself is 0. So can this be, how many roots will this have? What value of x px equals 0? None, exactly. But there is one case. What happens if a0 is 0? Then it would be 0 for all values of x. So it has lots of roots. So that's a problem. Our theorem has already failed. We have a polynomial of degree 0 for which, for all values of x. So how can we save this? How can we prevent this problem? Yes, we should not allow that. What?
A0 is not equal to 0.
Yes, but that's part of the definition of the polynomial. A0 is not equal to 0. When we defined a polynomial, we said that the term must not be 0. So if a0 is 0, then this is not a polynomial of degree 0 by definition. So this is again beautiful. It's not, as long as a0 is not 0, there are 0 roots. But what about the case when a0 is 0? Well, p of x equals 0 for all x. Every x is a root. There are infinite roots. But this is not a polynomial. What is this function? It's not a polynomial. Sine x is not a polynomial. So not everything is a polynomial. And the 0 function is not a polynomial by the definition of the polynomial. So whether or not it has 0 doesn't have anything to do with our theorem. So we have proven the simplest part, the first step, that a polynomial of degree 0 has 0 roots. There is no value of x for which p of x is 0. The second part is that the polynomial of degree 1 has exactly 1 root. So now this is also easy intuitively. I don't need to actually prove it. You should be able to see the theorem in your mind. So p of x is equal to ax plus b. A is not equal to 0. That's of course very important. That's what makes it. So what is a, by the way? A is the slope of the line. Yes. The slope is not allowed to be 0. It can be positive or negative. Regardless of what it is, the line is going to cross the x-axis, right? Because it has to go up or down. It has to cross. It can't prevent itself. So there has to be 1, 0. And there can only be 1, 0. There cannot be more than 1, 0. So now this is a very special case that the line must cross 0. I could show this on Excel, and I have actually some demonstrations. I'll show that later. So, but basically the reason for this, now we take this visual insight and we convert it into a little bit of more formal insight. I have to work on both fronts at the same time. So if you have a continuous function which goes from minus infinity to plus infinity, which is what the line does, as x goes to minus infinity, the line either goes to minus infinity or to plus infinity, depending on whether it's positive slope or negative slope. So it goes from minus infinity to plus infinity if it's a positive slope line. So it has to cross the 0 which is in the middle somewhere. This is called the intermediate value theorem. It means that for any continuous function, on any range going from a to b, if it takes some value at a and another value at b, then it must pass through all of the values in the middle. It cannot jump over any value. So if 0 is in the middle of minus infinity and plus infinity, then the function must take the 0 value. This is the intermediate value theorem, this intuitive understanding. You see, I was mistrained to believe that this is not. This is an intuition. And there is a formal proof. If you look at the formal proof, oh boy, you will not be able to understand. Because first you have to formulate what it means to be a continuous function. And the continuous function definition is quite difficult. It requires limits and infinities. And then you have to formulate this intermediate value theorem. And it's a very complicated theorem. So it's a misunderstanding to think that theorem and the proof is the intermediate. The intermediate value theorem is already, you understand it already. See? That's why you are already a mathematician. Because now how to express this intuition in formal terms, actually there is not one, there are many, many different ways of expressing this. And every one is just, the truth is already manifest in your mind, and now expressing, this is the system 1 truth. To put it into system 2, there are many different ways to do it, but it's all reflections of the reality. The truth exists in the intuition, and it's reflected in the reality in many different ways. Just like the true circle exists only in the imagination, and then every real world manifestation of it will be some imperfection, some imperfect picture of that truth. So every theorem and proof is an imperfect picture of the intuition that you already have, that you understand. So root of f, now this is the first time I'm defining a root. If any function f of x, r is a root if f of r equals 0.